One way that we can experimentally determine the rate law for an overall reaction is by doing initial rate analysis. Let's see how that works. So if we measure the concentration of one of the reactants as a function of time and do that for a particular concentration of the other reactant, we will get a curve that looks something like this. If we then do this same experiment, but use a smaller concentration of the reactant B, then we're going to end up getting a curve that decreases more slowly in time because we have a lower concentration of the other reactant B. So maybe this particular reaction was done with a concentration of B that's equal to 0.5 molar instead of 1 molar. Now, if we remember that the rate of this reaction is related to the derivative of the concentration of A with respect to time, and we have to make it negative because the A is a reactant and it's decreasing in time, and so the slope or the derivative of this curve, the slope of this curve or the derivative of this curve is going to be negative, down over, and so we put a minus sign so that our rate will be positive. Since the rate is the tangent to the curve, the derivative, we can draw a tangent to this curve and a tangent to this curve, and we'll do that at the initial time. So we're finding the instantaneous rate at time t equals 0. So the slope of these curves, if we determine the slopes, they will be equal to the rate at time t equals 0. So that is an instantaneous rate of reaction. Now notice that those rates are different, and they're different because we have different concentrations of the other reactant that we're not measuring the disappearance of. Okay, so let's see how we can use this type of data to determine a rate law for this particular reaction. Remember that we expect the rate to be proportional to the concentration of A raised to some power and the concentration of B raised to some power. Now, if we're looking at the instantaneous rates at time t equals 0, then we're looking at the initial rate, and that initial rate is going to be proportional to the initial concentration of A raised to some power times the initial concentration of B raised to some power. And the way we've designed this experiment, we know the initial concentration of B and we know the initial concentration of A. And if we've done these two experiments with the same initial concentration of A, then this has not changed in our experiment, and the only thing that has changed is this. So we can relate the rate, which we've measured by the slope, to the concentration of B, which we know, and see what we need to do as an exponent to make those two things equal to each other. Once we've done that, to find the exponent or the order with respect to B, we can do the whole thing over again, but measure the disappearance of B as a function of time and do that at different concentrations of A. So in other words, measure the instantaneous rate at time t equals 0 for a given concentration of B and different concentrations of A, and that will allow us to figure out the order with respect to A, because we'll know B, it'll stay the same. We'll just change this and we'll measure the instantaneous rate.